is a derivative of Dirichlet series. Of course, it's not an integer. Okay, take positive integer m. Sum over all m. Let me check this very fast. This sum over all m greater than or equal to m. Am minus lambda 2 minus sigma to the m. We want to compute our little f when s is equal to real number sigma between 1 and 0.9. Okay? So this sum, we will split the sum into the tail and the first few summands. So this thing is at most what? 3 times d1 squared, d2 squared, sum over all m greater than or equal to m. What? 2 minus sigma is at most 1.1, right? So we get 2.2 over 3, which is 11/15 to the small m, right? This is because sigma is between 1 and 0.9. So this can be estimated by 11/15 to the power capital M multiplied by the sum of the infinite geometric progression. So this is at most 3 d1 squared, d2 squared, 11/15 to the m multiplied by 1 minus 1 divided by 1 minus 11/15. This is 15/4. Right? So we have 45/4. This is at most 12. So it is smaller than d1 squared, d2 squared, 12 d1 squared, d2 squared, 11/15 to the m. Okay? So we estimated the tail. Now let us estimate everything else. Well, this will be rather obvious. F of sigma is equal to f of sigma, sorry, minus lambda over 1 minus sigma is equal to small f of sigma, which is equal to the sum over all m less than m, am minus lambda 2 minus sigma to the m plus tail sum over all m greater than or equal to m, am minus sigma 2 minus sigma to the m. And we want to estimate this thing from below, right? Okay, so this is at most this thing. And here am is non-negative. Am is non-negative, and this sum also contains the summand 1, right? So this is at least, let me write this down, 1 minus lambda sum over all m less than m, 2 minus sigma to the m. This is the trivial estimate for coefficients. Minus 12 d1 squared, d2 squared, 11/15 over m, right? And this stuff here can be estimated by 2 minus sigma to the power m divided by 1 minus sigma, right? This is the finite geometric progression. For finite geometric progression, you get this thing minus 1 divided by 1 minus sigma. Correct? Let me just compute it. Okay? Now this works. Choose m as follows. We want 12 d1 squared, d2 squared, 11/15 to the m be less than 1/2, and 1/2 to be at most 12 d1 squared, d2 squared, 11/15 to the m minus 1. What? What? Divided by? Divided by 1 minus q, right? Q minus 1. Q here is 2 minus sigma. Everything is correct. No contradictions in mathematics yet. Okay, so let's choose m as follows. The only limitation for m is that it is an integer, and you can certainly choose an integer with such a property, right? Okay, so from the first inequality, you conclude that this stuff is at most 1/2, and so f of sigma minus lambda over 1 minus sigma is at least 1/2 minus lambda multiplied by 2 minus sigma to the m minus 1 divided by 1 minus sigma, and you can cancel this thing out with this unit. So f of sigma is at least 1/2 minus lambda divided by 1 minus sigma, 2 minus sigma to the m. Correct? Sigma is between 1 and 0.9. S minus 1. S minus 1. 1 minus sigma. Yeah, you are absolutely right. Thank you very much. I missed the sign. This still works because you get minus lambda over sigma minus 1 here and plus lambda over 1 minus sigma. They cancel out, right? So you get this inequality, and to conclude our proof, we need to estimate 2 minus sigma to the m. Fortunately, we have the second inequality, right? So what do we get here? Well, 2 minus sigma to the m is equal to 1 plus 1 minus sigma to the m, which is at most exponent of m multiplied by 1 minus sigma, right? This is because 1 plus x is at most e to the x when x is not negative. Now we need an upper bound for m. Well, we have an upper bound. 15 over 11 to the m is at most what? 15 over 11 to the m is at most 24 multiplied by 15 over 11 d1 squared d2 squared, right? Okay? So m logarithm 15 over 11 is at most 2 multiplied by logarithm d1 d2 plus logarithm of this thing. Say you can replace it by 33. And our d1 and d2 are very large, so you can bound this from above by 2.1 logarithm d1 d2. So m is actually at most, everything here is just a numerical computation. 7 logarithm d1 d2. Okay? Now you plug this inequality here, and you get precisely d1 d2 to the power 7 multiplied by 1 minus sigma. Okay? This works. I told you something about this theorem on the previous lecture, but let me repeat. We established that if the class number is small, then we have a real zero of Ls chi close to 1, right? Suppose that Ls chi d1 has 0 beta with 1 minus beta smaller than 0.01, for example. If there is no such L function, then we already established that the class number tends to infinity, right? If there is some L function with this property, then theorem gives, what does it give? It gives f of beta greater than or equal to 1/2 minus lambda divided by 1 minus beta d1 d2 to the power 7 1 minus sigma, right? Or 1 minus beta, sorry. On the other hand, f of beta is equal to 0. From this, we conclude that Ls chi 2 should actually be larger than some constant multiplied by d2 to the power minus 0.07, say, divided by logarithm of d2. Logarithm of d2. Okay?
It is for every S?
Sorry, L1. This, how do we get this? From this, constant will be dependent on d1, of course. From this, you get that lambda is at most, lambda is at least some constant multiplied by d2 to the power 0.07, right? And this thing is constant dependent only on d1 multiplied by L1 chi d2 multiplied by L1 chi d1 d2. This stuff is estimated from above by constant multiplied by logarithm. So you can cancel this out and get this inequality, right? Correct? Or do you have any questions more?
Sorry, I didn't understand what we do with this high T1.
Once again, beta is fixed and dependent only on d1. F of beta is equal to 0 by definition, because it's product of zeta and L and so on. Our lemma gives this inequality. From this, you get that lambda appearing here is at least some constant multiplied by d2 to the power of minus 0.07, right? Now, this lambda is this product. This is a constant, right? L1 chi d1. It depends only on d1. This thing is estimated from above by a constant multiplied by a logarithm.
Okay.
That's it, okay? As I mentioned before, the largest downside of this result is that we established that class numbers tend to infinity. We established that there is no 11th discriminant, at least above 1 trillion. But this constant here is completely unknowable at all. So this estimate is kind of a qualitative one. So you get some constant, but you cannot even start to understand what this constant is. Okay, you can actually prove, Siegel proved that for any epsilon greater than 0, there is a constant C of epsilon greater than 0, such that the class number of minus d, the class number of d, where d is negative, is at least C of epsilon, absolute value of d, to the power of 1/2 minus epsilon. So essentially, class numbers should grow like a square root. But here, C of epsilon is, of course, once again, completely unknowable. This is the main source of ineffective results in number theory. Maybe next to, well, I don't know if anything is paralleled by this result. It's actually the main source. Okay, so we completed the proof of Hilbron's theorem. Let us switch the topic a little bit. I would like to also talk about Euler's ideal numbers or convenient numbers. По-русски они называются просто удобные. Okay, so what do we know about quadratic fields? Once again, we have d less than 0, fundamental discriminants. We have q of square root of d, and we know the criterion for prime number p to be represented by some quadratic form of discriminant d, right? When is p represented by some by some quadratic form? Is represented by a quadratic form of discriminant d if and only if we have what? Let's fix p to be greater than absolute value of d. When a large prime number is represented by some quadratic form.
It's 1 multiplied by 4.
What?
1
No. P should satisfy d over p equals plus 1. So Legendre symbol must be equal to 1. Correct? Because if you have, this is of course a necessary condition, because if you have a representation, then you have a non-trivial square root of d. No.
I thought that we can just solve it.
No, represented in integers. There are integers and a quadratic form that represent p. This result is Once again, let me remind you, zeta k of s is equal to zeta of s ls chi d. You can check that this formula actually implies that p is represented by some quadratic form if and only if we have this. This is equivalent, of course, to the statement that p is equal to the norm of some ideal in our field. Okay, in our, I mean, in ring of integers of our field. Okay, so this this quadratic character, the map n goes to d over n, Jacobi symbol, gives you a quadratic character of conduct absolute value of d. Quadratic character modulo absolute value of d, right? This is the direct computation follows from the quadratic reciprocity law. Okay, let's denote this map by chi d. Chi d is a map from z over dz star to plus minus 1. This is a homomorphism. Now, if our class number is equal to 1, then this is a very good news because you can easily derive that any prime satisfying this condition is actually represented by a principal form, right? It's a norm of a principal ideal. So it is represented as a norm of some element of your ring of integers. But what if you have class number not equal to 1? What will happen with representability of integers? Let's take, for example, discriminant to be equal to minus 20. What is class number of minus 20? Maybe someone will tell me very fast. So first of all, it is equal to 2. Yeah. There are